Hey there, and welcome back to this next lesson on higher level mathematics. Continuing algebra today, and we're looking at graphs and coordinates. So, what does it mean to plot the graph of an equation? What does that graph represent? How can we use them? Like, why bother? Like, what's the point of that? Um, we're going to look into all that today. So, few things we've got to look at. We're looking at axes first. So, this is what we plot our graphs on. So, and our coordinates. Then we're going to look at linear graphs. So that's basically the graphs of linear equations. Quadratic graphs, the graphs of quadratic equations. How do they differ? How are they similar? Then we're going to look at circle graphs, which is an important one to be aware of in higher level mathematics. Then we're going to just look at general other nonlinear graphs that you do need to be aware of and familiar with what their general shape is and their properties and how to use them, but you won't come across them as often typically. And then we're going to look at inequalities. So how do we express an inequality graphically? And how do they differ? How can we use, what we already know about, regular graphs, then, show inequalities. So lots of things to get through today. Let's look at axes first. So looking at the very beginning, axes. So typically we work with a set of two axes. I mean, you could have as many as you want, but at GCSE, we're only going to look at two. One going left to right, one going top to bottom like this. And we could plot a coordinate like this. And if we wanted to read off what is the value of that coordinate. So a coordinate, we write them relative to these axes. So what we do is we go down and we go across to our two axes and see what values they come to. So on the x direction, we've got 5, and then in the y direction, we've got a value of 10. So then if we had a coordinate like this and we had to plot it, how would we plot that? Okay, so x is 16, y is 17. So what we do is we draw a line at x equals 16, which is over there. These are all the points that are going to have an x value of 16. We go across, we can see all the values, all the coordinates that are going to have a value, a y value of 17. Where they intersect is basically where that coordinate's going to go. So we can put that there. So coordinates, graphs, they're a great way of visualizing the relationship between variables, which we would normally label as x and y on the axis like what we've done there. And so we have an equation like y equals x minus 3 like this. We draw the graph would look like this. And what that graph represents is it's basically, you remember going back to the very beginning of when we was studying algebra and we were trying to solve equations, and you see an equation of two variables we couldn't solve because you don't just get one answer. You get, I mean, you can technically solve it, but you're getting essentially an infinite number of possible answers. And that's what this line is basically representing, is all those potential answers. So uh, we, by looking at a graph like this, we can easily then see all the solutions of one equation. If we draw the graph of another equation, we can see all the solutions of that one, and then we can kind of compare them over time, or interpret them, or to scale them, transform them. So if we take a point like this that's on that line, and we can read it off as 10, 7, you can see that that is that would be a point on that line because y equals x minus 3. And here you can see 10, 7 basically is 10 minus 3. And you'll see that will be true for any point along that line that you select. So that's basically fundamentally what a graph is showing, which is important to be aware of because then it makes everything else make more sense, essentially. So we can extend these graphs because here we've just got positive x, positive y, but we could always make it like this and take into account negative values. Now, there's a really important point on a graph known as the origin, which is this point here, right in the middle, 0, 0. And this is the point from which every other point is being measured, or not measured, but like everything is relative to that point. So negative coordinates can be read and plotted in the same way. So let's plot in a bunch of points like this. We've got one in each of the quadrants for examples. And so this is how we define some kind of space, where we can view the relationship between two variables, or this could be coordinates like, say, on the surface of the earth, and we're, positioning where things are, for example. And what you need is you need an origin, and then you set your directions. We've got x direction, y direction, and then that allows us to then put the coordinates of everything else. So say that coordinate of minus minus 8, 3. What on earth does that mean? It means basically you're starting at the origin, you move 8 to the left and then 3 up. Uh, 3 in the, like 8 in the, the left of being the x direction. Same with the one, minus 15, minus 7. That basically means go start the origin again. You always start the origin and you're going 15 to the left and then 7 downwards, and so on and so forth. Every point in our space now is defined relative to that origin. So that is fundamentally what an axis is, what coordinates are, and what a graph means. So let's look at linear graphs. So a linear graph will always appear as a straight line. So we've seen linear equations before. And which is something when you just have y and x, but you don't have like an x squared or a square root of x or 1 over x or anything like that. It's just you just have y and x maybe multiplied by some number. So remember that the solutions of an equation correspond to two 2 points on the graphs. Okay, so right, 2 points on the of the equation is all we need to plot it, because it's a straight line. So say if you take a linear equation like this, and if we wanted to plot it, we just need to know 2 points that are going to be on this equation's graph in order to then plot the graph, because we could just then draw a straight line through those 2 points. So okay, where do we get those 2 points from? Well, we can generate as many as we want from this equation. So say if I just put in a value of x equals 0, I then get a corresponding value of y equals 3. I just substitute 0 into that equation. Likewise, I could substitute in x equals 5, and then I'll get a value of y equals 13. And so there you go. There's my 2 coordinates. I've got 0, 3, and then 5, 13 are my 2 coordinates. If I plot those 2 points, and because we know a linear graph is always going to be straight, because it's got this constant gradient essentially that makes it a straight line. There you go. That's all we need to plot it. So let's look at the equation of a linear equation in more detail. So you can put a linear equation in many different forms. We're going to see in the future, when it comes to simultaneous equations, we tend to work with a slightly different form. But here, it tends to be the most famous form that we often use a lot for graphs, because it makes it, we can then read off important values. Like here, we have it y equals mx plus c. So we get it in the form of y equals some number times x plus some other number. And those two numbers are important. Like m is going to essentially be the gradient, which defines how steep the graph is. And so it's basically saying for every one we go across, how much are we going up or down in the y direction? And then c is essentially shifting the whole graph up or down. And it determines where the graph intercepts the y-axis. And we'll see why that is in a second. So say if I have a graph like this, and we want to know what would be the equation of this graph. So we know the gradient is the rate of change. For every 1x goes up, we want to know how much is y going up or down. And so we could take 2 points on this graph. Ideally, we wouldn't want to just read off points, because it might not be completely accurate. But typically, you might be given 2 points like this. 4, 5, 12, 9 are 2 points on this graph. How do we calculate the gradient? Well, what we do, say if we've got 2 points A and B like this, and we're reading, the important thing is that we're reading from left to right. So we're reading from A to B, and we're trying to see, okay, what is the gradient in that direction? Because you see there, the gradient's going up. If you was to read in the other direction, you'd think the gradient's going down. So it's important to remember that we're reading from left to right. So we want to see what is the change of X going from left to right, and then how much is then Y changing in that same space. So here we can see X is going up by 8, and then Y goes up by 4. So X will always be going up because we're specifically reading left to right, and that's the direction X going up. But then the Y value could go up or down depending on whether the graph is going up or going down like that. We'll see that an example of that in a sec. So if we want to then calculate the gradient, we can do so like this. So it's the change in Y over the change in X. So this basically telling us for every certain amount of X changing, how much does Y change? And we can simplify that fraction to be 1/2. And we get this last coordinate down here. This is the y-intercept. So like I mentioned before, the c value corresponds to the point at which the value at which the graph intercepts the y-axis. And the reason why that is because think about it. Look at this, the general form, y equals mx plus c. This equation is the form of all linear equations, essentially. If you put x equals 0 into that, that mx term cancels out. And you're basically just going to get y equals c. And so therefore, that's why, at the y-axis, where x is basically equal to 0, you're going to get a value of c. And so that constant on the end is going to correspond to that value. So here we can see uh, it intercepts the y-axis at 3. So c is going to equal to 3. But say if we couldn't see that for some reason, or maybe we don't want to read off the graph because maybe it's not accurate enough. We want to mathematically calculate what that c is going to be. Well, we've got an equation of y and x plus some unknown constant here. We can kind of do similarly what we did before with when we was dealing with proportionality and was creating we had a constant of proportionality and that sort of thing in the previous lesson. Okay, if we just substitute in a particular point, it's like a boundary condition almost. We could then produce an equation of c. So say that pick any coordinate that's on that line that like assume we didn't know what the 0, 3 is. We could pick the point, say 4, 5. And if I put that in, okay, y equals 5, x equals 4, you see you get this. And if I try and solve that, you basically get c equals 3. So we see here, yeah, it is accurate to read off the graph, but sometimes it won't always be, or sometimes you won't have the ability to do so. So you see there, we get the equation of that graph being y equals half x plus 3. Now, say if we had a different graph going down like this, like quite steeply down, we could do the same thing if we had 2 points. We could calculate the difference in y over the difference in x. So notice now the difference in y is negative because we're going down. So that's very important. That's what I'm saying. You're making sure you're reading from left to right. We're going up 4 in x, but we're going down 12 in y. So difference y over the difference in x is going to be minus 12 over 4, which is minus 3. So we know the equation now is this, y equals minus 3x plus c. And now it's a matter of finding the c again, which it corresponds to the y-intercept. But you see in this example, because the graph is so steep, we can't see that y-intercept. That's going to be way, way up off the top of this graph. So this would be a case of where we would have to work it out from using a coordinate. So we could substitute in any coordinate, like I picked the one 16, 6. So x equals 16, y equals 6. Substitute those values in, and then we can rearrange to find c to be 54. So you can see the equation of this graph is minus 3x plus 54, or you could rearrange that to be 54 minus 3x. So that would be the equation of that graph. So generally we need 2 pieces of information to solve for a linear equation, where we either have 2 points, or we could have 1 point and the gradient, or say if we was given the 1 point and the y-intercept, we could then calculate things. If you was given the gradient and then the y-intercept, then it'd be very straightforward. You could just write the equation out straight away, couldn't you? So you wouldn't get something like that. But yeah, generally you just need 2 pieces of information like that, and then you can work it out. Now, remember what the equations represent, like these graphs of the equations, sorry. They represent all the solutions to those 2 equations. So, say if we wanted to find out where they're both simultaneously true, it's going to be this point in the middle. And this is one use of graphs that we could do. We could try and read off where that coordinate is, and we'll get a rough estimate of what values of x and y that both these equations will be true at the same time. And if you plug those values into both equations, you'll find they'll come out to roughly true. Not exactly because it's an estimation, like we just read off the graph. If we wanted it exactly, we would have to mathematically solve these 2 equations simultaneously. And this is something we're going to do in a future lesson. But you see, this is like a graphical interpretation of that. Next, say we're looking at perpendicular graphs. So say if we have a simple one like this, y equals 2x, and so there's no plus c because it's essentially going through the origin, so c is 0. We've got y equals 2x here. And say if we had a point like this on the graph, and we wanted to know what is the equation of this perpendicular line. So perpendicular meaning it's cutting at 90 degrees. How would we do that? Because we haven't got 2 points now. So we can't do what we've done before, but we do still have 2 pieces of information. We have one point on the line, and we have the fact that it is perpendicular to this line y equals 2x. So that's our second piece of information. But how do we use that? Um, well, there's an important relationship between the gradients of perpendicular lines, which we can use, which becomes our second piece of information that we need. So uh, that perpendicular line is going to have the same form as usual because it's a straight line. But the gradients of perpendicular lines always multiply to get -1. Um, and yeah, it's a relatively simple proof for that that you could look up, or I might show at some point. Um, but we just need to remember, to know this result and how to use it. You wouldn't be expected to prove it. So you see here, the gradient of the green line is 2, and the gradient of this new line is this unknown m. We know 2 times m is going to be -1. That's the key result that we need to be aware of. Perpendicular gradients multiply to produce -1. So we can use that, and that gives us the gradient now because we can just solve for m. So we've got the equation is this. Now we can use our second piece of information, the point on that graph. That point where they intersect is a point not just on the green line, but it's also on the yellow line. So we can use that. Substitute that into this equation for the yellow line. X equals 6, y equals 12, put it in, rearrange, solve for c, we get 15, which you can kind of see reading off the graph, but you need to be familiar calculating mathematically because you can't always do that. Or at least not accurately necessarily. So that's an example of using perpendicular lines, which we need to know how to do. That will be important later when we're working with circles. So we're looking at quadratic graphs now. This is an important one. We'll do a lot on quadratics. So drawing a quadratic. Uh, so this would probably be quite straightforward for you guys at high level. So say if we have a function f of x, and we replace the output. So the output of fx, we make that equal to y, and so we can just plot that on our usual x, y axes. To plot a curve is a bit different to a straight line. Like a straight line, we just need 2 points, and then we draw a straight line through it. But a curve is kind of constantly changing. The gradient isn't just some constant number where which makes it straight. It's changing. So what we have to do, we have to generate a whole bunch of points like this. And so we pick a whole bunch of values. So we're plotting x between -4 and 4. So what we do is we write a list of all x values, not well, all of them, like a few of them, and we can then calculate the corresponding y values as so by substituting in our x values. So you just got to be careful when substituting in, like say the x squared -4 squared. So the minus is included in that. So it's going to be +16, not -16. With the minus x there, you've got -4. So that's going to become +4. Just be wary of those sort of things so that you calculate things correctly. And the positive ones that down there will be a little bit more straightforward. Substitute them in, use your rules of BIDMAS. You might want to try it for some of the others, but if you calculate them all out, you'll get something like this. And then here's a bunch of coordinates. We have -4, 14 as one coordinate, -3, 6 as another, -2, 0 as another. And if we plot all of those, you can see a shape forms. And this is a very common shape for quadratics. They're always going to have this kind of shape where it's either U like this, or sometimes it will flip upside down and you'll get an N like that, and like an N shape like this. And that occurs when the x squared coefficient is negative. It causes the whole thing to flip up. But here, x squared is positive, so we have this classic U shape. And when we draw a line through it, it is important that you do a nice smooth curve. Don't like get out a ruler and draw each point together with straight lines, because that wouldn't be correct. That's like a linear graph is straight. And so it's like you're doing a whole series of linear graphs. That wouldn't be correct. Like it has to be a nice smooth curve because this is a curve. Um, so yeah, just bear that in mind because you could potentially lose a mark for that in an exam if you start drawing it together with straight lines. You've got to draw a smooth curve through them all. Right. So here, say if instead we wanted to just sketch it, because sometimes we do this. We don't need to get a very specific graph and plot it exactly. We just want a rough sketch and we want to know key points. So you might get something like this. Like you look at y equals x squared minus x minus 6. So the uh, coefficient of the x squared is positive. So we know it's going to have this U shape. And it's probably going to intersect the x-axis at some point. It might not. And well, it definitely will intersect the y-axis at some point. And say if we just wanted those points, those key points, where does it intersect the axis? We've already calculated them here, but say if we didn't know them, how would we calculate them? So uh, we can calculate that information by substituting x equals 0, and you see we get, you know, y equals -6. So that's going to be the y-intercept. Same thing like with a linear graph. That constant on the end is going to be the y-intercept, because whenever you substitute in x equals 0, the x and the x squared term are just going to disappear. So that's one thing that the linear equations and quadratic equations have in common. The graph crosses the x-axis when y is 0. So that's when we're at the x-axis is when y is 0, isn't it? So if we substitute in y equals 0, we get this. And we've seen this before. We know how to solve this. If we factorize, say, for example, you can use any one of your methods, but I've used factorization here because we can. And you then get your two solutions, x equals -2 and 3. And you can see that is where it intersects the x-axis. So we've got that. We also can find this point down here, which is a turning point, because it's the point at which the graph turns. So you see the graph is going down and it gradually goes up, and there's a point where it kind of turns around and now it's starting to go up again. And it's that moment where the graph is essentially flat. Like, it's not going down, it's not going up, it's just flat. This is a really important point, which you've learned a lot more about this kind of stuff in things like calculus at A level, if you're doing A level math at some point. At the moment, we learn how to do a turning point essentially using completing the square. So we saw that technique last time. If you apply completing the square here, and we could rearrange it like this. So we've basically got y plus something equals x plus something squared. When you've got it in this form, the turning point is essentially going to be the negative of those two values that I've got there in those two numerical terms. So y is going to, the x coordinate is going to be at positive half, and the y coordinate will be -25/4. And the reason why that is got to do with something called transformations of graphs, which we haven't looked at yet. So you'll learn why that is later in this course. But for now, know that that is how you can calculate find where that turning point is you complete the square and rearrange it like this, and then you can just read off the values, which is really handy. So that's going to be that coordinate there. Okay, so let's look at the discriminant. So we looked at this last time, like mathematically, what does it mean? We saw that it corresponds to the number of solutions that the equation has. When, you know, what that quadratic, when we set it equal to 0, how many solutions does that have? So, okay, this quadratic, first of all, we can calculate those roots as -4 and 3. We could calculate where the y-intercept is. Well, we can just read it off from the equation, can't we? It's going to be +12. We could even calculate the turning point. You know, you might want to pause here and try and find that for yourself using completing the square. Now we've seen the discriminant is this value here from the quadratic formula, which corresponds, you know, b squared ac, you know, that corresponds to the coefficients of the quadratic. So let's take a closer look at that. And you see here, if we calculate the discriminant, so b is -1, a is -1, and c is 12. Plug that into b squared minus 4ac, and you get positive 49. So positive value, that tells us we have two real solutions, which we can see here on the graph. Like we saw when we calculated the roots, we get two roots, two intersections with the x axis. So that's what the discriminant means graphically speaking. It's talking about how many times is it intersecting the x-axis, because that's when the quadratic is equal to 0. So it's going to be how many solutions there are to that equation. So if we see two intersections in this case. If we take a different example like this, so I've done a different quadratic now, you see how it kind of just comes down and it doesn't intersect the x-axis, it just touches it and goes up. And if we calculate the discriminant of this, you see it comes out to 0. So that's that middle case where you have one unique solution. So you see, it's like it's not really intersecting the graph. That's why I put intersection in inverted commas there. It just comes down, it touches it, and then it goes back up again. That's that critical case there where the discriminant is specifically equal to 0. Now, when it's less than 0, it would be something like this. And we can see that with this one if we try and calculate it. So you see, Ed, something like x squared plus 4. Don't let that confuse you. That because you might be thinking, oh, what is the value of b then? Like the coefficient of the x term. Well, there is still technically an x term there. It's just like 0x. So b is basically just 0 in that case. So we can calculate the discriminant as usual. 0 squared minus 4 times by a, which is 1, times by c, which is 4. We get minus 16. And you see that negative value means there's no solutions to this equation equaling 0. There's no roots. And so what that means is this never intersects the x-axis, which we can see here when we plot the graph. So graphically, that's what that represents, the discriminant. And you need to be able to use that that information with various problems. If you, like what we saw before, you could calculate like an unknown if you're told the equation only has one solution, which is the one they commonly like to use, because you see that means the discriminant is equal to 0. So the equation, that the discriminant then will produce an equation that you could then solve. If you gave one of the others, it then produce an inequality, which you could be asked, but it tends to be less common in my experience. So let's move on. So we've done linear graphs, quadratic graphs. They're the two big ones that we're going to spend most time working on. So let's look at circle graphs now, which is another big one that we need to be aware of. So this is an example of a circle, or like on an axis. Obviously, you know what a circle looks like. So it has this equation, x squared plus y squared equals 9. And okay, what does that mean? This is essentially x squared plus y squared is equal to the radius squared. And so we can tell that the radius of this is going to be 3. And you can see that. So radius is basically the distance from the center to the edge of the circle, if you're not aware. So we've got this, and this equation can actually make a lot more sense why a circle has this equation when we look at something known as Pythagoras' theorem. If you're aware of what Pythagoras' theorem is, x squared plus y squared equal to radius squared should be looking very familiar to you, and you might want to think about why there's that similarity. You could get something like this. Unlikely in my experience. So it's kind of similar to what we had with the turning point before, where we've got the same equation or a similar equation here, but we're kind of adding something to the x and the y, and it's essentially transforms the graph. So here we've got it's equal to 4, so the radius is 2, and what these values that are being added to the x and the y essentially shift the graph, so that the center, not being at the origin 0 0, it's at the point 2 minus 1. So you see it kind of shifts it in the same way as we saw before with the turning point. So it's, yeah, I can't get into too much explanation as to why that is. Something to be aware of. We'll look at that more when it comes to transformation of the graphs. Most of the time we see something like this, where it's centered on the origin. So this is what we need to be most familiar with. So say if we're at a point like this, and a common question we might be asked is that we want to try and find a tangent to circles, because tangents are really useful. And say if we've got a point on the circle, and we know we want the tangent at that point, so that's the point here that just kind of goes and just touches the circle at one point and keeps going. It doesn't intersect it, really. We can calculate that, what the equation of that tangent circle is. It's kind of similar to the scenario we saw before with perpendicular lines, where we've got the same kind of problem. Like we want to find the equation of a circle, the equation of a straight line, sorry, but we only have one point on that line. So that's only the one piece of information. But the second piece of information we have is that it's a tangent to this circle. And it's like, okay, how can we use that? Well, what we can do is instead we can calculate this radial line. And if you're familiar with your properties of circles, that radial line is going to hit the tangent at a right angle, which is perpendicular. And so we can use that. If we can find this radial line, we could then find the tangent line, like doing it the same way we did before. So, okay, let's instead think, how can we find the equation of this radial line? So we can do that in the way we normally do, because we've got 2 points. We've got the point at which it touches the tangent, which is minus 2 root 5, but it's also going to go through the origin at 0 0. So we see that gradient reading from left to right is going to be 2 and then minus root 5 down on the y. So it's going to have this equation. If we do difference y over difference in x, we can see that c is going to be 0 because it's going through the origin, and so the y-intercept is 0, so c is going to be 0. So here we go. This is the equation of the radial line, but we don't even need that. All we really need is that gradient, because then we know the tangent line is going to have this gradient. because we know they have to multiply to produce -1. And if you maybe do a quick calculation there, you'll see that minus root 5 over 2 times by 2 over root 5 will cancel to -1. So we know that's going to be the gradient of the tangent line. Now we're in business because we know what the gradient is. We just need to find out what C is. We can't really read off, where it intersects the y-axis accurately. We can see it's a bit over 4. Um, so what we have to do is work it out by instead uh, substituting in a point. And the only point we have is the point -2 root 5. So we put in the value of -2 for x, the value of root 5 for y. You see the gradient here. I've rationalized the denominator there by times in the top and bottom by root 5. But it's the same thing. And so you just need to be able to use your understanding of surds to rearrange this, and you get C equals 9 root 5 over 5. So you could put that into your equation there, and it's not a very nice equation. Tangent lines often won't be, because a circle is a bit more of a complicated equation. So you see we get y equals 2 root 5 over 5x plus 9 root 5 over 5. We could perhaps simplify that a little bit, but I'll just leave it like that for now. So you see, it's kind of building on a lot of the skills we've learned. So they can be some more challenging graphs there. Right, so let's finish up on other nonlinear graphs. So there's just some other ones that you don't get asked too much about, but you do need to be familiar with them because you can get asked. Say like a cubic graph, which looks something like this. I would recommend going on to like an online graphing calculator. I use this one called Desmos, which is DESMOS, where you can type in equations and you can mess around with them and it will just instantly plot them, and you can get a feel for what different types of graphs look like. So this is a cubic graph where you've basically got an x cubed term and it changes the way the shape goes. Rather than it going down and coming up once, it turns twice like this. It's going to have 2 turning points and, 1 or perhaps 3 roots. It depends on how it goes. Uh, you see it's going to then shoot down on the left, but shoot up on the right because the x cubed term is going to essentially dominate as you get into bigger x terms. And so, as x gets more, large positive, x cubed is going to shoot up to positive infinity. And when x is like going negative, it's going to shoot down to negative infinity. So that's why it has that general shape. As with polynomials, the y-intercept can be read off because, it's just going to be 1. And we could have a different one like this, where you see that, again, it flips the graph if you negate the highest order term. So in this case, that's the x cubed. The x cubed term, you see if I've put a negative sign in front of it, it flips the equation upside down, the graph upside down. And you can see with this one as well, this is an example of one that only has 1 root, because you see it only intersects the x-axis once. That second time it comes up, it doesn't actually quite hit it. So yeah, just sort of, looking, maybe plotting an x cubed graph, like a cubic equation, and reading them, just kind of interpreting them. That's so general skills you just need to be familiar with. You could have something like a reciprocal graph like this, y equals 1 over x, which is an algebraic fraction. Like the simplest one is one like that. And it's going to have asymptotes, which are like these red lines, these red dashed lines I've put in, which are like examples of convergence, where a line, it comes down and it's gradually approaching that line, but it never quite reaches it, which makes sense. Like you think about it, as x goes really big, going on to like infinity, y is going to get smaller and smaller because y is equal to 1 over x. So if you have 1 divided by some really big number, y is going to be really, really small, but it's not going to be 0. It will just keep getting closer and closer. You could get other ones like this that are a bit more complicated. Again, you won't be asked too much on things like this, but you might be asked to just maybe plot it for a series of points or, to interpret in some way. You can see that this one has 2 asymptotes like this, at x equals -2, which might make sense because, if you put x equals -2, you're essentially going to divide by 0. You might want to think why there's an asymptote at y equals 1 there. Like maybe try putting in y equals 1 into that equation and try and solve for x and see what happens. And it might help you understand why there's an asymptote there. But yeah, typically you're only really going to be looking at more basic case like this with algebraic fractions. But you see how it has these interesting properties. Another one is an exponential graph. This one tends to be more common of these sort of more obscure graphs that you encounter less often. This one seems to be the one that's the most often, if that makes sense. So you might have something like this, like y equals 2 to the power x. So this is when x is the exponent, it's exponentiating, however we want to phrase it. So it's always going to have this kind of shape where it's just kind of it just shoots up to infinity in the positive direction. In the negative direction, it's going to converge towards zero. So you see it has this asymptote at x along the x-axis, essentially. You see it's always going to intersect the y-axis at 1 because you think, okay, when is x 0? Any number to the power 0 is always going to be 1. So it always intersects at 1. Um, Now you can see these properties are very much the same, regardless of what that base is. So we see 3, 4, 5, 6. It's the same thing. It just the steepness changes. Uh, you might again try it like in the graphical calculators, the like online graph calculator that I mentioned. You could see what happens when the base is less than 1, like between 0 and 1, or perhaps even if you want to see when it's negative, but that it can make things go a little bit more crazy. Um, but yeah, so that's an example of exponential graphs. So finally, let's take a quick look at inequalities. So yeah, bear with me here. I know this is going quite a long lesson, but there's a lot to get through here. So we've got inequalities. So it's just basically going to apply a lot of what we already know. So say if we have a linear equation like this, and we've got a straight line that represents all the the solutions to that equation, all the values of x and y, such that that equation will be true. But say if we had something like this, like y is less than this, what would that look like? So that's going to correspond to a region of the graph. It's not just a specific value, is it? It's anything less than that. So this line basically divides the space up into two regions. You've got this region here, you've got this region here. Which one is the correct one? Well, this line represents when y is equal to 27 minus 3 over 2x. Well, when y is less than this, it's going to be down below because y is up and down, isn't it? So if we want when y is less than this, we need to go down. So it's going to be this area here. So with an inequality, a question would ask you to shade an appropriate region. And so you have a line is going to kind of divide the space into two or more regions, and you need to then shade the correct one. And we can confirm this is correct by picking a point in and out of that region and try substituting them in. So if I substitute in the 0.65 to that inequality, we get 5 less than 18, which is okay. Good. But if we put in 1610, I get 10 is less than 3, which is wrong. That's not true. So you can check that you've done it right. You've picked the right region. So we can take another example like this. If we have the equation y equals x squared plus 4, we could plot the graph just as usual. But now say we're trying to consider the inequality when y is greater than x squared plus 4. We can apply the same logic. Okay, when y is greater than this, we want all the area above the curve. And again, we can confirm that by taking a point in and out of that area. Put it in, put in the point 110, all good. Put in the 0.25, no, you get 5 greater than 9, which is incorrect. So we know that's not part of the region. So we can always check our answers like that, which is great. Say if we plotted another one, we've got y equals 4 minus x, but we want the region when y is less than 4 minus x. So similarly, we're going to get everything below the graph. And you can see that both are going to be true when x is less than 0, at least on the graph, the axes that we've drawn here. Some of you might notice that if we went into far negative x numbers, eventually there'll come a point when that area is going to close. But here you'll see that red region. So if you had to shade the region such that both these inequalities are true simultaneously, you'd shade that red region there. So you could always see it like simultaneous inequalities. So let's look finally at, say, a quadratic inequality like this. Like if we just wanted to find when the values of x such that this expression is going to be greater than 0, this quadratic expression. So first of all, let's get it to just our usual form. Like we don't want that negative x squared. So let's multiply through by -1 to change that to positive. Remember your rules of inequalities. If you multiply through by a negative number, it's going to change the sign of the inequality. So we've got that there, it's flipped around. We could then factorize this in the usual way, but it's a little bit different now because before we can't just say, oh, x plus 3 is less than 0, x minus 1 is less than 0. It doesn't work like that because before we was talking about when they two numbers multiply, when do they equal 0? Only, which is only when one number is, equal to 0. But in this case, we're looking at when they're less than 0, which is not 0, is when they're basically negative. So that's why we still want to put it, get it to the form of something less than or greater than equal to 0. Because now we're basically considering, okay, is it positive or is it negative? We've got two things here multiplying to produce something that's less than 0, so that's negative. So we uh, we know what that must be. Either one is positive and the other one's negative. So x plus 3 is positive, say. Say if we had that, if x plus 3 is positive and x minus 1 is negative, then that would multiply to produce something that's negative. And we could then solve each of those, to get these two inequalities. But we could have easily have done it the other way around as well. Like we could have assumed x plus 3 was negative and x minus 1 was positive. You might be able to see that that's not possible, but in case you're not, like we would just have to consider that and see which one's right. So one way we could do that is mathematically by taking a point. So, okay, we've got our roots of minus 3 and 1. Let's first of all pick a value in between those two. So 0. I just pick a convenient one between minus 3 and 1. And you see it all checks out. So if I substitute 0 back into our original quadratic, I get 3. And 3 is greater than 0. So we're all good. But if I substitute in the value of 2, which is outside of, that range, that's greater than 1, we get the value minus 5, and that's not greater than 0. So that shows that must be wrong. And so the first one must be the correct one. And that we can actually combine together to something like this. X is greater than minus 3 and less than 1. A different way, and sometimes a better way to do it, is to think of it graphically. And so this is where it's important to be able to um, roughly sketch a graph, because you don't want to draw this out exactly. But we know the roots are at minus 3 and 1. So you see here, and because the coefficient of the x squared term is negative, we know it's this N shape. So we get this N shape where it intersects the x-axis at minus 3 and 1. And we basically want when y equals when y is greater than 0. So we've got here where y equals, minus x squared minus 2x plus 3. So we know when it's equal to 0, it hits those roots, at minus 3 and 1 there. We want when it's y greater than that, we can see it's going to be this region here above the x-axis. And we can see that occurs between x equals minus 3 and 1. So that's another way of getting that solution there. So you can do it graphically, or you could just do it mathematically by comparing different values to see which one is correct. But you see there, it's using a lot of the same skills we've already done. You just need to be mindful of that point when we factorized it and we got x plus 3 times x minus 1 is less than 0. Generally, you will be given something that can be factorized, and you need to know how to deal with that. It's not just going to be, oh, one's less than 0 and the other one's less than 0, like we do before when it's equal to 0. Like the same logic doesn't work. So yeah, just be wary of that. Right, so let's leave it there. So yeah, long lesson there today, looking at all different types of graphs. So I'll leave you with a little did you know here that there's a thing we often do when we're dealing with like highly nonlinear graphs, something that might be curving a lot, and we simplify it by making it a series of linear graphs. So say if I've got like a simple graph like this, and I plot, or a simple axis, and I plot, this quite complex graph, and it's curving all over the place. Something we can do is actually break it up into a series of little straight lines like this. Like this is something we people do a lot. I've used this a lot in my career, and you can see for the bit where it's curving quite smoothly, it's quite accurate. But the problem is you see that little bit in the middle where it curves a lot, it actually starts to become quite pointy in places. So this little approximation isn't so good unless maybe we make those little lines shorter. And this is a great thing, like if you're trying to get a computer to do some complicated calculations with graphs or with equations, because you're breaking up into lots of little lines, and you've got to calculate all those little lines. But it's only a linear line, and a computer is very, very good at doing something like that, where you're calculating something. Perhaps you put that into a function, and you get to repeat that function over and over again, and you can calculate all those little lines. So that's a handy technique right there that's used in the real world that you might want to be might find interesting. So here's our takeaways for the lessons. Make sure you're familiar with graphs because they're a very powerful tool, and you're going to be asked plenty of that in your exams. Um, the key properties of graphs, what exactly graphs are at their fundamental level. Um, right. So now next time we're going to be looking at simultaneous equations. So I mentioned that earlier, which is basically like corresponds to the intersection of two graphs. We're going to look at how we can mathematically solve that exactly. So I will see you next time for that.